Hello, everyone. I hope you have a good day, good morning. Let's start. Today, I'm going to talk about vector valued functions. It is part of the exam. It's the part of the exam we will have next week on Tuesday. And so let's continue. If you have extra time this week, I'm going to solve some potential problems which we might see in the exam. So let's start by vector valued functions. Okay. So the first thing we need to look at is the plane curves. And then space curves. So what do I mean by a plane curve? Well, basically I mean, look at the plane R2. There's x-axis and y-axis. A plane curve is anything of this form. It's just a curve which goes around. So let's say it starts at some point and then it gets to this point, right? That's just a plane curve. It doesn't have to be graph of a function. It can be anything. Well, what is the most basic example? Lines are the most basic examples, probably the most basic examples of plane curves. So a plane curve is a function. Well, maybe I show it with R, which is, its domain is either real numbers or a subset of real numbers, and its image is the plane. I would show the variable in the domain by t, where t stands, well, kind of for time. And R of t tells me, the way we can think about it, it's not a bad way to think about it, is that where a particle is at time t. So for example, we can assume we have a particle at time 0, this particle is here, or at time 0. At time 1, this particle we can think is here. At time 2, the particle is here, and etc. Okay. So let's look at a few examples. Let's see the difference between an equation. The first thing we need to understand is the difference between an equation and a parametrization of a curve. So when we have a curve, we might describe it with an equation, or we might parameterize it as a curve. Let's see the difference. Look at this line. Look at this line. Let's say we have a line. Let's look at the line which passes through the origin, line which passes through the origin 0 and 0. And another point, let's say 1 and 1. Okay. First, what is the equation of this line? Well, it's simple. The equation of this line is, this is this line. The equation is just y equals x. This is the equation, right? This is equation of this line. There is no time t. We don't know where a particle might be, a particle which would walk along this line, where this particle might be at time t. Parameterization, maybe I should say, there is not a unique parametrization? A parametrization is a way of saying where a particle would be at each time t. Okay, so here, for example, I can write down x equals t and y equals t. Both of them, they are equal to t. What does it mean? It means if t is 0, x is 0, and y is 0. So at the time 0, the particle is here. If t is 1, it means x is 1, y is 1. So at t equals to 1, the particle is here. If t is 2, x is 2, and y is 2, so the particle is here. So it's one parametrization of this line. And this parametrization says the particle is moving in that direction. Right? But you might take another parametrization. Someone else might look at the same line and says, no, my particle is moving in the other direction. That direction would give you another parametrization. There is another parametrization which via that parametrization, the particle would move in the other direction. So we can look at the same line, y equals x, and take a different parametrization. We might say x equals to minus t, y equals to minus t. This gives us the same parametrization. Why? Well, let's see. If t is 0, x is equals to minus t 0, y equals to minus t 0. So at t equals 0, the particle is here. What about at t equals to 1? What about after 1 second? Well, x equals to minus 1, y equals to minus 1. So after 1 second, the particle is here. What about after 2 seconds? Well, x is equal to minus 2, y equals to minus 2. So the particle would be here. And if we connect these, we can see we would get the same line, but the particle is going towards the other direction, right? Let's look at another example. Let's look at the equation of a circle centered at the origin with radius 1. The equation is this: x squared plus y squared equals 1. That is the equation of a circle centered at the origin. But this doesn't tell us anything about time, right? There is no time. There is no particle moving along this circle. Well, there is one parametrization we have, a standard one. If I take x to be cosine of t, and if I take y to be sine of t, what would I get? I claim this is a parametrization for this circle. First, let's try a few points. Let's see where the particle is when t is 0. If t is 0, x is cosine of 0. What is cosine of 0? It's 1. Y is sine of 0. What is sine of 0? It's 0. So x is 1 and y is 0. It's here. X is 1 and y is 0. So at t equals 0, this parametric equation, if I had a particle which was following this parametric equation, at time t equals 0, the particle would have been here, right? What about t equals, well, let's take another thing. Let's say pi over 6, for example. X would have been cosine of pi over 6, which is the square root of 3 over 2. And y is sine of pi over 6, which is 1 over 2. Okay, where is that? Well, it's here. This is t equals pi over 6. The particle would be here. Where is the particle at t equals pi over 2? Well, x is cosine of pi over 2, which is 0. Y is sine of pi over 2, which is 1. X is 0, y is 1. So it's here. So particle is here at t equals pi over 2. So the particle is apparently going around the circle in counterclockwise direction. So it is one parameterization of this curve. It's counterclockwise parameterization of this curve. Another person might parameterize the same curve. Another particle might go along the same curve, but in the other direction. Right? Just one simple fact. Why this thing, why, let's show it with star. Y star is really parameterizing this circle. It means I should show y star implies this equation x squared plus y squared equals 1, because this is the equation of circle. And it's simple because, well, x is cosine of t, y is sine of t. Circle means x squared plus y squared should be 1. But what is x squared plus y squared? X is cosine of t, so it would be cosine of t squared. Y is sine of t, so it would be sine of t squared. But cosine of t plus sine of t squared is always equal to 1. So x squared plus y squared is equal to 1, which means this is a parameterization of the circle. Okay. Okay, so this is an example of parameterization of a curve. Okay. Any question?
Yeah, question.
Yeah, sure.
So the actual parameterization, so obviously you can with cos t sin t because of the trigonometric identity, but is there like other stuff with regards to other shapes like that we're gonna have to know in order to come up with the parameterizations, if that makes any sense?
Yeah, so sometimes you can use the same thing sometimes to find parameterization of slightly more complicated things too. So for example, suppose rather than a circle, suppose you have an ellipse like this. Which is given by the equation. Suppose we have this curve given by the equation say x squared over 4 plus y squared equals 1. So in that case, this is not a circle anymore. Here x goes up to +2 and -2. Y goes only up to 1 and -1, right? Now, I might ask you, find a parameterization for this curve. Find the question is find a parameterization for this curve. Okay, what does it mean? It means this curve is given. This curve is given. The question I would ask you is that, give me a way to describe a particle moving along this curve. So this is an example of an equation. What we are looking for is a parameterization. So parameterization, well, in more concrete words. Parametrization means you should tell me what is x, what is y as functions of time. So you should describe a particle which goes along this curve. And you should tell me where the particle is at each time t. Okay, so that's the question. That's the meaning of parametrization. Parametrization means a curve is given and we have an equation for it. X squared over 4 plus y squared equals 1 is an example. And parametrization means you should give me x and y as functions of time, which means you should tell me where we are, what is x and what is y at each time t. Well, the idea to do this thing is completely similar to the previous one. Well, here x squared over 4 plus y squared equals 1, right? So I can rewrite it as x over 2, the whole thing squared, plus y squared equals 1, right? So x over 2 squared plus y squared equals 1. Well, there is an equation which I know and I like it, and that's the fact that cosine of t squared plus sine of t squared equals 1. Right? So if this thing wants to hold, one idea is that what I have here, it can be equal to cosine of t. So basically, this equation is the key equation, which we are going to always use. Key equation. Okay, so here x squared plus y squared equals 1. If this thing wants to be true, one way is that x over 2 would be equal to cosine of t, and y would be equal to sine of t. If that's the case, x would be 2 cosine of t, and y would be sine of t. And that is a parametric equation of this curve, because it tells me where is x, what is x and what is y at each time t. And that would give me the position of the particle. So first note that here, x over 2 squared plus y squared equals 1. So the whole x over 2 should be cosine of t. And let's see how it works. If t is equal to 0, for example, what would I get? I would get, maybe it's better to write here. If t is 0, x would be 2 cosine of 0. Cosine of 0 is 1, 2 times 1 is 2. Y would be sine of 0. Sine of 0 is 0. So the point would be 2 and 0. This is the point. So this is where the particle is at t equals to 0. Okay, where is the particle at t equal to pi over 2? Well, x is 2 cosine of pi over 2. Cosine of pi over 2 is 0. 2 times 0 is 0. Y is sine of pi over 2. Sine of pi over 2 is 1. So the particle would be here. So from here it goes there, and then later it goes there, and we can continue. You can try more values for t to find x and y and connect them to see if this is the ellipse you're going to get, right? So that's how we find a parametrization for a curve in a plane, right? That's the way to do it in the plane. Now, the second step is to do it in three-dimensional space. That's what we are mainly interested in. So we can have a curve in three-dimensional space. A curve in three-dimensional space would be something like this. So for example, particle is there at time t equals 0. It might be here at t equals to 1. It might be here at t equals to 2. Might be here at t equals to 3, and etc. Okay, and we want to find an equation which describes a given curve. Okay. So the first interesting curve we have in three-dimensional space, so in space curves, the first thing we are interested in, again, is a line, but we already have seen a line as a parametric curve, right? Remember, for example, when we have a line which passes through 2 points, say 1, 1, and 1, and 0, 0, 0, there are two ways to describe this line. One way was, well, to find this vector v, which in this case would be 1, 1, 1 minus 0, 0, 0, which is just 1, 1, 1. And the equation would have been x minus one of the points, say 1 over 1 equals y minus 1 over 1 equals z minus 1 over 1. That would have been the equation of the curve. This curve here is a line. This is an example of equation, right? But there was another way of describing the same line, and that was what I call parametric equation or a parametrization. What would have been the parametric equation of this line? Well, remember x, y, z, they would be equal to the first point, 0, 0, 0, plus this vector here, 1 times t, plus 1 times t, plus 1 times t. So it's something in terms of time, in terms of t. So for example, if t is 0, x is 0, y is 0, z is 0. So at time t equals 0, we are here. If t is 1, we would be here. X would be 1, y would be 1, t would be. So it's a parametrization of this line. It tells us where the particle is at each time. So the different two equations we had for a line, things we've already seen. One of them is an equation of the line. The other one is kind of time parametrization of the line. Let's look at the second interesting example. The second interesting example in space is helix. Helix is something like this. So if it's x, this is y, this is the z. Helix, it looks like this. It goes around the z-axis. So it's, well, if you haven't seen this before, it's very, very similar to the structure. You might see the double helix structure of DNA. The double helix structure of DNA is very similar. It's something which rotates, for example, upward here. This is called a helix. What is the equation of this helix? The thing is that if you look from above, if there was a source of light here, the shadow of helix on XY plane would have been exactly, for example, well, either a circle, or more generally, it would have been an ellipse. So if a particle moves around this curve, it goes up and up and up and up. If we look at its shadow on XY plane, if there was a source of light here, we could look at the shadow of this particle on this XY plane. It would have moved along this circle, its shadow. So suppose the shadow really is the unit circle. Suppose the shadow is the unit circle. Okay, then the equation, the parametric equation, or a parametric equation for this helix would be what I'm going to write for you. So x, here I should tell you what is x, I should tell you what is y, and I should tell you what is z, and I should tell you what of these things in terms of time, as functions of time. So one example is x equals cosine of t, y equals sine of t, and z equal to t, just t. Let's see why this thing describes a helix. So x equals, the claim is that this parametric equation, x equals cosine of t, y equals sine of t, and z equals t, the claim is that this thing describes a helix. Okay. So the point is that if we just look at cosine and sine, if we just look at the first two variables, x and y, it means if we completely forget about the direction of z, we have x equals cosine of t, y equals sine of t, but we already know what is this parametric equation, what it's describing. It's just a circle, right? It would be a circle in xy plane. But on the other hand, there is another variable. There is this variable z, and z equals to t. So when t is 0, the variable z is 0. So we are here. When t is 1, the variable z equals 1. So we should be in this plane. So as time passes, we go upward because z is equals to t. Z is kind of the height of the particle. So as time passes, as t goes forward, we go up. But on the other hand, the first two things tells us x and y, they behave like a circle. So they are like a circle. They go around this axis like a circle. But on the other hand, at the same time, the height is increasing. So they should go around like a circle, but at the same time, the height is also increasing. The result would be something like this, which we call a helix. Does it make sense? Is it clear to you? So if we just look at x and y, we would think we would have something like a circle, something which just goes around like a circle. But the third variable tells us z equals to t. Therefore, as time is passing, the height is as time is increasing, because z is equal to t, z is also increasing. So x and y, they are like a circle, but the height is also increasing at the same time. And this is the curve you are going to get as a result of that. Okay.
So question.
Yes.
How do you know the scale factor between z and t, like in relation to one another? How do you know that it's one in the equation?
Yeah. So I mean, this is one example given. So for example, someone might ask me, what is the curve this equation describes? So sketch this one. X equals 4 cosine of t, y equals 4 sine of t, and z equals to 3t. Okay, this is another example with different factors. I want to see what is the curve described by this equation. So find or sketch the curve described by this parametric equation. Okay, how can I find it? The idea is that when we look at three-dimensional space, x, y, z, it's usually better to first kind of ignore one of these variables. So I would first ignore this variable because x and y here, they look pretty related, right? So I would ignore this variable. So for me, x would be 4 cosine of t and y would be 4 sine of t. Therefore, x over 4 is equal to cosine of t, and y over 4 would be equal to sine of t, right? Now let's write down the key equation. I told you the key equation is cosine of t squared plus sine of t squared equals 1. Right, that's the important thing. But cosine itself is x over 4, and sine itself is y over 4. Therefore, x over 4 squared plus y over 4 squared equals 1. Therefore, x squared over 16 plus y squared over 16 equals 1. Therefore, x squared plus y squared equals 16. What is this equation? This is the equation of a circle with radius 4, right? This is equation of circle centered at the origin, radius 4. It means if I didn't have the z-axis, what I would get would have been a circle in xy plane. Forget about the z-axis. This is a circle in xy plane with radius 4, right? But now I have a third parametric equation, and that's what tells me what is the height at each time t. So for example, when t is 0, okay, it's better to go to next page. So this is x, y, z. And I know the equation is for x and y is x squared plus y squared equals 16. So here, if I look only at x and y, I would get a circle with radius 4. But there is also z, and z is 3 times t. So let's see what we have at different times. If t is 0, z would be equal to 0, x would be equals to 4 cosine of 0, y would be equal to 4 sine of 0. Cosine of 0 is 1, sine of 0 is 0, that's what we would get. So at time t equals 0, we would be here, 4, 0, 0. Let's look at another time. Let's see where we are at t equals, say, pi over 6. Well, x would be 4 cosine of pi over 6, which is 4 times square root of 3 over 2, 2 times square root of 3. Y would be 4 sine of pi over 6, which is 4 times 1 over 2, which is 2. Z would be 3 times t, which is 3 times pi over 6 or pi over 2. Well, pi is 3.14, so it's slightly larger than 1. So where is this thing? 2 square root of 3, almost somewhere here. And then y is 2, and z is slightly above 1. So the point we are looking for is almost here. So at t equals to pi over 6, we got to this point. So our curve, maybe a little more towards the right. It should be 2. So maybe almost here. This is where we are at pi. This is where we are going to be at t equals pi over 6. So the curve would get there at t equals pi over 6, and it goes around and around. So there are 2 important things in these equations. So x equals to, let's look at the parametric equation again. x equals to 4 cosine of t and y equals to 4 sine of t and z equals to 3t. There are two or three important numbers here. One of them is the number here. The number here gives us the radius of the circle. So when you have a helix like that, if we just look at its shadow on the ground, we would get a circle. That circle has some radius. That radius is written here. It's 4, for example. The number here tells us how fast we are going to go up, towards up, around this helix. So if this number here is 3, for example, in 1 second, we go from 0 to 3. It tells us how fast we go towards up. So look at these two different examples. It can climb the other axis too. I would explain that. So look at this helix. So look at this one and look at this one. Which one is going up faster? The left one or the right one? Yes, that is true. So the point is that when I want to understand how fast it goes up, what does it mean? It means if I look at, so as I said, if I look at the shadow of helix on the ground, I would see a circle. Here, this circle. So if I want to see how fast it goes up, I should see if I go around this circle once, where would I get in the z direction? So here, if I go around this circle once, in 3-dimensional space, I would get to this point. Here, if I go up, if I go around the circle once, I only get to this point, right? So when we have z equals to 3t, or we have z equals to just t, it means if I go around the circle once, like that, where would I go? Where would I get? How much does it take to go around the circle once? Does anyone know? How much does it take to go around the circle once? Exactly, 2 pi. Circle, it's 0 here. If we go around, get there, it's 2 pi. It takes 2 pi seconds to go around the circle 1 complete time. So if I go around the circle by 2 pi, I would get to this point. And in 3-dimensional space, this point corresponds to this point here. Now, if z equals to 3t, z would be equal to 3 times 2 pi, which is 6 pi. So the height here would be 6 pi. But if z equals to t, and t equals to 2 pi, z would be only equal to 2 pi, which is here. So the number here in front of t shows how fast this thing is going up. So if it goes up very, very fast, this number would be a large number. Okay, let's go back. So if we are going fast, this number would be a large number, like 3t. If you are going slowly, you see, now it takes a long time for me to get there, right? If I have to go around many times, it means it takes a long time for me to increase the height. So z would be, for example, t over something even, say over 5. What about the other direction? This can go down. What would be the equation for z if it's going down? Can you guess?
Negative.
Exactly. So it would be, for example, negative 2t. Right. What would be the equation for something like this? a helix like this. Well, here we have changed the roles of y and z. So here x would be something like cosine of t, z would be something like sine of t, and y would be something like 2t, right? So for example, if I ask you to just give a sketch, not sketch very carefully, just very approximately, sketch this thing. X equals to t, y equals to cosine of t, z equals to sine of t. What would be the direction of this helix? It would go along which variable? Well, you should say the variable of time. Yes, exactly. So it would be something like this, right? It would go along the x variable. So that's how almost you should kind of think about these curves. Helix is a very important one. And one other thing I should tell you is that the kind of cross section of this helix doesn't have to be a circle. Here the shadow is a circle. We might have another helix where the shadow is not a circle, like this one. If we look at the shadow of this one, we might see something like this. Okay, how can I see that in the equations? Well, the equation of the one on the left side, this one, might be something like this. Cosine, well, say 2 cosine of t. Yes, that's correct. 2 sine of t, and z might be t. It means when I have 2 here and here, it means I have a circle here with radius 2. But here I might have 2 cosine of t, y equals 4 sine of t, and z equals to t. It means if I look at here, the shadow would be an ellipse, and it has 2, if I look at 2 directions, oh, I would bring it here, I would draw it more carefully. I would have here 2 directions, one in direction of, oh, sorry, it's the other way around actually, 4 and 2. If I look at the direction of x, this radius would be 4. If I look at direction of y, this radius would be 2, right? It's not a circle anymore. They are going to be different. Okay. Well, I wouldn't tell you what you would see in the exam, right? But it's not going to be hard. If you understand what I'm talking about, you would be able to manage the exam too. Okay. So, but the things you need to know is that first of all, if I give you an equation, first you should be able to find its parametric description. If I give you a curve like this thing, you might guess sometimes what is the parametric equation. If I give you a parametric equation like this one, you should be able to sketch it. These are the different things we need to understand, and we would learn them one by one. We would look at the examples. Okay. Now, for a moment, what would be the normal equation of helix? Well, in general, a helix in direction of z, for example, that would be something like this. X would be a cosine of t, y would be b sine of t, z would be c t. It means we have a helix in direction of z. If we look at the shadow, it would be an ellipse here. The radius in direction of x would be a. Oh, I see. radius, the radius in direction of y would be b, and the speed in direction of z would be c. Okay, there's a good question. Someone has asked, what is the equation of the helix? Can we write down an equation for helix, not parametrization? That's interesting. Well, we can. So let me address this question. So suppose x is, well, 2 cosine of t, y is 3 sine of t, and z is just t. This is a parametric equation. Can we write down an equation which is just an equation, so without the time variable, without t? Can we get rid of t? Just write an equation in terms of x, y, and z. Well, look at these two. First of all, you can say x over 2 equals cosine, and y over 3 equals sine. And remember, the key equation says cosine of t squared plus sine of t squared equals 1. Therefore, here cosine is x over 2, sine is y over 3. These two squared equals 1. So that's one equation. What about z? Well, z is equal to t. But what is t? Look at one of these equations. For example, the first equation. X over 2 is cosine of t. At least in one, well, you know, we are going around the helix many times. It's a little maybe advanced to talk about it now, but at least locally, if I don't want to go all above the helix, maybe in a small amount, like small length of the helix, I can write down t as arc cosine of x over 2, right? Now z is equal to t, therefore z is equal to arc cosine of x over 2. And this is the second equation. These two equations describe this helix. But the correct word for that, which this is not the topic of this course, this is, yeah, we need two equations, definitely. So first of all, we need a system of equations to describe helix. So we need two equations here, not one. First of all, when you have one equation, okay, let me explain that later. Let me just say one more word about that. And the second thing is that this defines this helix only locally. Remember, arc cosine makes sense for the angles between 0 and pi. So from 0 up to pi, it makes sense. After that, it really doesn't make sense. We should write down another equation, two other equations for this part, from pi to 2 pi. And then we should write two other equations from 2 pi to 3 pi, and etc. That's something I don't want to get to. That's more related to a topic named manifolds, which actually this course can be thought of as a study of manifolds in more basic cases. But anyway, that's not what we're going to talk about.
I have a question.
Yeah.
Sorry, just to clarify, so like on the midterm, you're only gonna ask us, like you'll give us like in the format x equals a cosine t, y equals b sine t, z equals ct, right?
Yeah.
Okay.
Yeah.
Okay, got it.
That's something you might see. Yeah. So I want to add one other thing. Why we had two equations? Well, when we are in three-dimensional space, R3, if I just give you one equation, anything, what do you guess? Just a random equation. This is actually an equation which you have no idea about, right? X cubed, you haven't seen this equation before. But if you want to guess, what do you think it would give you? Do you think it would give you a curve or it give you a surface? what would be the dimension of this equation? Would it be something one-dimensional or something two-dimensional? Would the image of this thing would be something like this thing, or its image would be something like a surface, or maybe even more complicated surface? Yeah, so when I give you one equation, you usually get a surface. If I give you two equations, if I give you another equation, it would give you a curve. That's the case. One equation, usually, one equation gives you a curve. Sorry, one equation gives you a surface. If I give you two equations, which are supposed to hold at the same time. So for example, look at the equation of a line. It says x minus, say, x minus x naught over a equals y minus y naught over b. There is another equation equals z minus z naught over c. There are actually two equations here. This one is equal to that one. This one equals to that one. And if I give you three equations, you should guess the answer in general, usually, again, not always, usually. If I give you three equations, the answer would be just a couple of points, right? That is always true. Yes, okay. Well, that is usually true. The correct mathematical word for that is that in a generic case. Okay. Now, another topic we should speak about, we should think about is, well, representing graph of a function as a curve. Graph of a function in plane as a curve. What do I mean by that? Well, look at graph of a function. Say y equals x squared. Okay, this is graph of this function, but also it's also a curve, right? I can imagine a particle moving along the graph of this function, right? It goes there, goes there, goes up, just walks on this graph of this function. So I want to find a parametrization for the graph of y equals x squared. The answer is always simple. Whenever you have graph of a function, you should say what is x as a function of t, what is y as a function of t, right? Okay, I would tell you the answer. The answer is pretty simple. When this is y is a function of x, right? Note that here y is a function of x. When y is a function of x, we call x the free variable. It means x is not function of anything itself, right? Y is a function of x, but x itself is free. We always take the free variable to be equals to t, okay? And if x is equal to t, y is equal to x squared, x equals to t, so y would be equal to t squared. That would be the parametrization of this equation. So for example, if I wanted to find a parametrization for the graph of this function, y equals sine of x, yeah, independent variable is another word for that. I would have said x is the free or independent variable. Y would be sine of x, which means it's sine of t. It might be the other way. So we might have x equals y squared. The graph of, you see, this is x, this is y. X equals y squared would be something like this. We've changed the roles of x and y. If they ask us to give a parametrization of this thing, I should say x equals y squared. Here, x is a function of y, right? Here, here, y is a function of x. Therefore, x is the free or independent variable. If x is equal to y squared here, I would say x is a function of y, and y would be the free and independent variable. The time parametrization would be, I would take y to be equals to t, and x is y squared, therefore t squared. That's how we find a parametrization of graph of a function as a curve. Okay, now let's get to more interesting problems. If I have two surfaces inside a three-dimensional space, what would be their intersection? So for example, not a line, well, you're correct, you're very close. Rather than a line, we would say a curve, because their intersection doesn't have to be straight anymore, but it is one-dimensional. So suppose we have this cylinder. And suppose we have this plane. What is the intersection of these two? What is the intersection of this cylinder and that plane there? Well, the intersection would be something like this. I hope you can visualize. Maybe it's better to do it like this. The intersection would be something like this, right? If you have a cylinder and you have a plane, which the plane is normal orthogonal to the cylinder, the intersection would be like here, it's like this. It looks like a circle. Is it clear to everyone? Can you visualize this? Okay. But what if the plane is not really completely orthogonal to the cylinder? So what if we have a cylinder and another plane? What would be the intersection of these two? What will I get? What is the intersection of this plane and this cylinder? It would look like something like this, actually. It's an ellipse. So we get to a very important topic, that curves can appear as intersection of surfaces. And that's what we want to do now. Okay. Okay, so suppose let's see a few examples. Let's start from the first one, the one we saw earlier. So suppose I have a cylinder and I have a plane. Suppose the cylinder is given by the equation suppose cylinder is given by the equation x squared plus z squared equals 1. And plane is given by the equation y equals 0. What I would want you to do, for example, in the exam, sketch these two surfaces. Okay. show the intersection on the graph, show the intersection. Write down the equation of the intersection. Find a time parametrization. Well, the intersection would be a curve. Find a time parametrization for what we call the intersection curve. I would solve this one for you, but before that, I want you to think about it for a few minutes. Follow these steps yourself, okay? I would give you 5 minutes. I want all of you to try this, try to sketch them, find the intersection, write down the equation, and then find a parameter. That's a complete question for you. We have surfaces here, we have curves, we want to find the equation, we want to find the parameterization. All of you try, and then I would explain step by step how to do it. Is there any equation? Sorry, is there any question before doing that? Okay, if not, think about it. Okay, so does anyone have the answer? Okay, that's good. X squared plus y squared equals 1. Well, I don't think so, because, well, here it says y is equal to 0. So y should be always equal to 0. So if x squared plus y squared equals 1, it means x squared, y squared would be 0, so x squared would be always 1. X squared plus z squared. But you're right. You've made just a small, tiny mistake there. Yeah, I guess probably it's x squared plus z squared equals to 1. Okay, I'm going to solve it. Ready? Or you want to think more? Is there anyone who is in the middle of solving it and want me to wait a little more, or I can do it? Okay, let me do it. So x squared plus z squared equals 1 and y is equal to 0. The first step is to sketch these two surfaces. Well, this is our three-dimensional space. Let's look at this thing. This equation, it doesn't have y variable, no y variable. Whenever there's no y variable, we understand it's a cylindrical surface. Okay. What is its cross section? How does this cylinder look like? Well, if I look at x and z, x squared plus z squared equals 1 is the equation of a circle with radius 1 centered at the origin. So in terms of x and z, so here this equation is written in terms of x and z. So I should look at the xz plane. So I have, this is x, this is z, this is xz plane. X squared plus z squared equals y, 1 is the equation of circle with radius 1 in that plane. So kind of like this. And because it's independent of y variable, we would get a cylinder on above that, kind of like this. And the cylinder is always in direction of the variable which is missing. Here it's y. Okay, that's one of the surfaces. Actually, it goes to infinity. The second equation, oh, it seems you missed a class, right? So, well, one idea is you can go and look at the recorded video of lecture 4, but a cylindrical surface is a surface which, well, just let me give you just one example. Well, one example is what we have here, just a cylinder, but it's not just cylinder. So if you think about any of two directions, say x and y, you can think about a curve in that plane, right? Let's suppose y equals x squared. That looks like this. Now, a cylindrical surface above this curve means just suppose you're just moving this curve in direction of z, right? And it would trace out a surface. So if I move this thing in direction of z in three-dimensional space, it would trace something for me. It would look like this. That's something we call a cylindrical surface. So here we have this curve. We are moving it in direction of y, and we look at its trace when we are moving it in direction y. When we move this one in direction z, its trace would be something like this. Okay, these surfaces are called cylindrical surfaces. Okay, good. So, but go and watch the video for chapter 4, section 4, okay? Okay, anyway, so here we have this cylindrical surface. And then there is another surface, y equals 0. Well, what is y equals 0? This is x, y Z. Y is 0 on this plane. Anywhere on this plane, this is X, this is Z. Any point on this XZ plane, the Y is 0 there. So Y equals 0 actually is the plane made with this axis XZ. Let's call it XZ plane. Now, intersection of this cylinder and this plane, so this is this XZ plane, their intersection is exactly this circle here. Okay, so let me go to the next page. Okay, so now we have this cylinder, we sketched this cylinder, and then we have this plane, and then their intersection is this thing. Intersection means these two equations, they are correct at the same time. So x squared plus z squared equals 1, and y is equal to 0 at the same time. So what is the equation of the curve? Actually, what you need to say is the equation of the curve is exactly this thing. You know, a few of you said this is the equation of the curve. This is not equation of the curve. If you just say x squared plus z squared equals 1 is equation of the curve, well, x squared plus z squared equals 1 is the equation of cylinder, not a curve. Remember, a curve is given by two equations, not one. One equation gives us surface. So one equation gives us surface. Two equations give us a curve. And three equations gives us points. Four equations, what would be four equations? Can anyone tell me? Usually, what would be if we have four equations?
A point.
Sorry?
A point.
Well, empty, it's better to say. Nothing. And the equation of the curve would be x squared plus z squared equals 1 and y equals 0. Yeah, just that. You know, I gave you two surfaces. The equation of the curve of intersection is these two equations. It would be the first equation and the second equation at the same time. And the last step was to find a time parametrization for them. Well, this circle, you know, it's a circle in terms of x and z. So x can be cosine of t, z can be sine of t. What about y? Well, y is 0. It's mentioned here. So because x squared plus z squared equals 1, this tells us x can be cosine of t and z can be sine of t, because cosine of t squared plus sine of t squared equals 1. And y can be 0.
Why are you using three equations if it's a curve?
Okay, these are not three equations. This is the parametric equation. Remember, parametric equation means tell me what is x as a function of time, tell me what is y as a function of time, and tell me what is z as a function of time. That's parametrization. That's not the equation, right? That's what we mean.
So then what in the question, did you mean write down the parametric equation?
Well, I exactly mean this red box. That
so the parametric equation.
That is
right?
this is the parametric equation.
Yeah, I know, but it just in the question it just said write down the equation. So are you asking for the parametric equation?
No, for both of them. So when I tell you write down the equation, the step number 3 was writing the equation. This is the equation. Just the equation
which
of
is
the
x squared plus z squared equals 1 and y equals 0.
Exactly. I gave you
and
two
then
surfaces. Yeah.
Yeah, and then the parametric equation would be what you wrote in the box.
Exactly. So
Okay,
this is the answer of step 3. This is the answer of step 4. Exactly. Exactly. Well, let's do more examples. Let's make sure we are not confused.
Just 1 second, real quick. The y equals 0, is that necessity to keep in the parametric equation answer, or
Say again.
can you omit the y equals 0 in the answer?
No. You should in parametric equation, you should tell me what is x, what is y, and what is z.
Okay, all right, thank you.
Yeah, okay, good. So let's look at another example. Okay, let's see another example. So the parametric equation is always relative to time. Yes, parametric equation is always, that's the meaning of, so parametric equation means write down an equation which describes what is x, what is y, what is z in terms of time parameter, which here is t. That's what we mean by the parametric equation. Exactly. So let's look at another example. Let's see. So suppose we have two surfaces. Again, let's say x squared plus y squared. Well, let's have more variety. Okay, suppose you have two surfaces, x squared over 12 plus y squared over 24 plus z squared over 4 equals to 1. This is one surface, surface number 1. We have another surface, surface number 2. Cylindrical equation given by this, cylindrical surface given by this equation, y equals x squared. So sketch these two surfaces. Show the intersection well, intersection on the graph. Yeah. Okay. Find the equation of the intersection curve. Find parametric or parametrization of the intersection curve. Okay, so think about it for another 5 minutes, and then I would solve it for you.
I have a question.
Yeah.
So I'm having a hard time like visualizing what like the graph of what this would look like, or like what a lot of stuff would look like sketched out. Are there any like websites that you recommend for like just trying to graph it out so I can get a sense of like what something looks like?
Yeah, there was a website I used the other time. Also, I wrote its link in your in the notes. In the notes I uploaded last week. It's well, I can write it here. monroecc.edu. It's a web page of a college, I think, or university. And then if you just search this thing, if you search it, oh yeah, okay, calc plot 3D. If you search these two things together, on the web page of this college or university, there's a web page that you can just write down the equations and it would sketch them. I can use it now, actually. That's a good idea. Okay, so let's start with sketching the surfaces. X squared over 12 plus y squared over 24 plus z squared over 4 equals 1. First of all, we should understand what is the type of this surface. What kind of surface is this? Yes, that's an ellipsoid. So if this is our three-dimensional space, there are, well, a few different things to understand about the ellipsoid. First is its center. The center of ellipsoid, well, in general, an ellipsoid would be of the form x minus x naught squared over a squared plus y minus y naught squared over b squared plus z minus z naught squared over c squared equals 1. The center of such ellipsoid, the center is x naught, y naught, and z naught. A comparison shows us here the center is the origin, 0, 0, 0. Because we have x minus 0 squared plus y minus 0 squared plus z minus 0 squared. So the center of the ellipsoid, the center equals 0, 0, 0. An answer to the question, what happens if I'm a horrible sketcher on the test, is that it's good if you show all of your work. For example, it's good that if you think from your sketch, I wouldn't understand that the center of your ellipsoid is 0, 0, 0. It's good that you tell me that you know the center is 0, 0, 0. So even if your sketching is not very good, I would know that you know the answer. Okay, that's the first thing about an ellipsoid. The second thing is how much it's extended in each direction. So a squared is the denominator here. Look at that here, is 12 in our case. So a is the square root of 12. We should point out that point on the x-axis. Well, what is square root of 12? Almost. What is the value of it? 3 point something, right? 3 point what? Does anyone know? I think 4. Yeah, thank you. 3.4. So say 1, 2, 3, 3.4. Let's show that point here. It would be useful. Let's show this point here. Okay. The second denominator is b squared. B squared is equal to 24. Here we have 24, right? So b would be square root of 24. What is that? Almost. What is the approximate? Yeah, 4.8. Well, let's show that on the y-axis. 1, 2, 3, 4. Well, here 4.8, somewhere around here. And finally, we have c squared. C squared is equal to 4. So, okay, I know this one. C is equal to 2. 1, 2. Our ellipsoid is the ellipsoid which passes through these points. It might be hard to sketch it, I know. I'm not a good sketcher myself, but it really doesn't matter. It's just a sketch. We are not computer. We don't need to be very accurate. It's just a sketch. So the ellipsoid would pass through these points, so it should be something like this. Yeah, as you can see, I'm not a good sketcher either. But anyway, it's something which passes through these 3 points we found. Okay, that's one of them. That's one surface, right? Then we have another surface. So this is the sketch of first surface. Is there any question here how we do this?
Wait, is there another point on like why is there another point on the y-axis and another point on the z-axis?
Well, I mean it's symmetric, right? Like a circle. If it passes through this point, it would pass through this point too. If it passes through this point, it would pass through this point too. It's exactly, it might not be obvious in my drawing, but it's like a sphere or an ellipsoid. They're symmetric. Yeah. So
excuse me, I wonder if it's symmetric. Does it mean like we taking in the x-axis, we are taking the 3.4, right?
yes.
So we have to also we also have to taking the negative 3.4.
Yeah, this is, although my picture is not good, this is negative 3.4. This
Okay.
is, for example, 4.9. This is minus 4.9. Yeah, you're right. Yeah, this is 2. This is minus 2. Yes.
So in this case, for all the ellipsoid plane, like they are all symmetric in 3 points, right?
Yeah. So yeah, there's a good comment. Maybe it was better for me to say it like that. When a squared is 12, what is a? A is plus or minus 12. That's a good comment, actually. So, right? When for example, when c squared is 4, c would be plus or minus 2, right? One of them is here, the other one is here. Yeah, thank you, Mary. So,
right,
yeah, good. So we have these points, and then we should try to connect them. And I know that we can never really sketch these things very well. It's fine. Just you should also in the exam, you should mark all these points and then kind of try to connect them. I would understand what you're trying to do. I think we are all better in, maybe we are better in imagining these things rather than we really kind of drawing them on a piece of paper or anyway. Okay, so that's one of our surfaces. We have another surface. So one of our surfaces is this ellipsoid, which looks like this. Maybe it's even better to do it like that. Okay, so here we had our ellipsoid. Here was 3.4. Here was 4.9. Here was 2. That was the first surface number 1. Now we have another surface. Surface number 2 is y equals x squared. Now there is no z. Therefore, whenever one of the variables is missing, it would be a cylindrical surface in direction of the missing variable, in direction of z. So y equals x squared. It's something in terms of x and y. This is x, this is y. Y equals x squared, we know its graph. It looks like this in xy plane. And then we should consider the cylindrical surface in direction of z. We can continue in both directions. it would be something like this, right? So if I want to sketch both of them in the same space, the other one would be like this, right? We have surface number 1, we have surface number 2. Okay, can you see the intersection? Can anyone, well, this goes from behind the ellipse line. Can anyone see the intersection? Can you imagine what is that curve, which is the intersection of these two?
Is it a helix?
Sorry?
Is it a helix?
I didn't understand. So what we are looking for is that we have two surfaces. The intersection of these two surfaces would be a curve, a rectangle. That would be strange because these two things, they don't have any kind of corner, but the rectangle has a corner. A disjoint curve, that might be true. It's not necessarily one piece. It might have different so-called connected components. So let's see how, well, I can sketch it for you, but probably you wouldn't really understand my sketch. Okay, I would sketch it for you. The sketch would be something like, the curve would be something like this. And
is it two curves?
I think it's going to be one. I think this is going to be the curve. So this is the part which is towards us. And then there is a part which is on the other side of the ellipsoid. Now I would show it to you. Okay, let's see how we can see this thing. So let's try to sketch it on the computer. Yes, ellipsoid has volume. These are some random questions, right? Yeah, that is true. We would talk about it in chapter 4. Okay, so let's try to sketch these with computer. So what is the equation? X squared over 12 plus y squared over 24 plus z squared over 4 equals 1. Let's isolate z, okay? So z squared over 4 is equals to, I would erase this surface because we already have it on the other, in the other graph. Okay, so z squared over 4 would be 1 minus x squared over 12 minus y squared over 24. If I multiply everything by 4, z squared would be 4 minus x squared over 3. Oh, we are multiplying by 4. Minus y squared over 6, right? Therefore, z would be squared plus or minus square root of 4 minus x squared over 3 minus y squared over 6. Okay, this is what this is the equation we have here for z if I try to isolate z. Okay. Now I want to sketch this on computer to see if I can see this thing better. Let's see. Let me try. Okay. So here z is equal to 4 minus x squared over 3 minus y squared over 4 square root of that, right? That's one part of our ellipsoid. Okay. Now we should add the other part too, the minus part, right? So we need to add another equation, which is basically the same thing with minus, because z is plus or minus this thing. If we took the squared root, so it would be plus or minus. So together they would give us this thing. Okay, that's one surface. We have another surface, right? We have another surface, which was the cylindrical surface. Y equals x squared. Y equals x squared. Okay. Let's have that. So it would look like this. I'm not sure how you can see it, but this is, we have two surfaces here. Oh, here it says add to graph. If you look at this, if I click here, it would give me a list. I'm not sure how good the quality is. I hope the quality is good enough. But here it says functions, z equals something, x equals something, y equals something. You can choose y equals f of zx. Yeah, you're welcome. So, yeah, this is something you can try yourself. So let me see if we can make it a little, the number of. Okay, so you can see the intersection here along this. This is the intersection curve. Do you see these points where they meet each other? This is the intersection. This is the curve which we are looking for. You see, it comes here and then gets to this point, and then comes here, and it looks connected. It doesn't look disconnected. It seems it's only one piece, right? It goes along here and goes along there. See? So it seems to be, well, it seems to me that this is a connected and we can see the curve here. Yeah, this is the edge of kind of the sphere here. Well, the edge of the sphere is not the correct probably word to use for it, but yeah, you're right. This is exactly the thing which we see. This is like the edge. This is the part which they are meeting each other. That's there's a curve there. The way they have intersection, that's the intersection curve. Okay, so let's go back. Okay, so I hope that would give us a better picture of what's going on here. So let's go back. So we had, so suppose we have these two surfaces. This is one of them. Then there is another one. And their intersection would be a curve which kind of, I guess, looks like this. That's what I saw. Well, I mean, it's really hard to be sure. I don't necessarily expect you to find that's a little hard. That's the hardest part of the question, really, to find the intersection. Yeah. Normal vector of the surface. Wait, I'm not 100% sure what you mean. Let me finish this thing and then you can explain more what exactly you have in your mind. So we have, okay, so we have these two surfaces. We have the intersection. Now let's go back. So what is the equation of the curve? Well, as I said, the equation of the curve you should say is just the equation of the first surface and the second one. This is the equation of the curve. And that's it. Now, the next step is to find the parametric equation. Okay. So in order to find the parametric equation, in these questions, this is kind of complicated question. You need to find the free or independent variable, or choose a variable to be the independent variable. What do I mean by that? Well, here y is a function of x, right? So y is not free. Y itself is a function of x. So here x is the free or independent variable. Look at the first equation. The first equation also tells us z squared over 4 is 1 minus x squared over 12 minus y squared over 24, which means z is plus minus 4 minus x squared over 3 minus y squared over 6. So here we see z is a function of x and y, and y itself is a function of x. So the free variable, the independent variable is x. Z is a function of x and y is a function of x. So everything is a function of x actually. So the free variable is x, okay? So when we find what is the free variable, we set that free variable to be equal to time, t. Okay, so our equations, one of them is z is equal plus minus 4 minus x squared over 3 minus y squared over 6, and the other one is y equals x squared. So if x is equal to t, what is y? Well, x is equal to t, y is equal to x squared, so y is t squared. What about z? Z is plus or minus square root of 4 minus x squared over 3. But what is x? X is t. So it would be t squared over 3. Minus y squared over 6. What is y? Well, y itself is t squared, so it would be t squared squared over 6. And that would be the parametrization of this curve. What we have here is the parametrization. Okay, any question? Now, I got a question which I'm not sure if I understand. What do you mean by normal vector of the surface here, or intersection curve?
I'm not sure about that, but if we find like basically can normal vector represent a plane? Like if we find the normal vector of one plane and of another plane, and find their cross product, or I can't remember that cross product, or with the angle between them is something like that, can we get the intersection curve, something like that?
Yeah, no, we can't actually use that. So things you're saying are correct, that we can use that to find the angle between surfaces and curves, but not for finding intersection. So for finding intersection, we should follow this strategy. So yeah, so if it doesn't make sense to you, I would solve a few more examples. but this is the way to do these kind of questions. Okay, any other question? Everyone's happy with this? Okay, let's
I have a
yeah,
clarifying question. Why did you choose, like, why did you say z is a function of x and y? Because if you had solved differently, you could have said like y is a function of x.
Yeah, you're right. You're right. I could have done that. Y would be plus minus something, right?
Or is it because you knew that for y equals x squared, that y was a function of x, so you just chose to do it that way?
Yeah, yeah. So the point is that I want to write y in terms of t, right? That's the goal. What is the goal? The goal is to be able to write everything in terms of t. So I already knew y equals x squared, and I already knew x is t. So y would be t squared. I know what is y. I don't need to do anything about y anymore. I wanted to find what is y in terms of t, and that equation already gives me what is y in terms of t. I'm not looking for y anymore. The unknown now is z, right? Does that make sense to you?
Yeah, it does. Thank you.
Yeah, good. Okay, let's have a little break. Let's maybe come back, I don't know, 11:05. Is that good? Okay, let's have a little break and then we would continue with limits and continuity.